So moving into section 6.2, we're going to get into our next big thing, where we're looking at getting confidence intervals for mu without knowing sigma, which is a far more reasonable situation in my opinion, where instead, if we don't know sigma, we have to use its best point estimate as a replacement. We have to use S. But remember that S always has a bit more variation than sigma ever does. S is always a little bit worse in some sense. And to take care of the fact that what we're working with is not quite as good as what we would like, we can't use the normal distribution in the way that we would like to. So instead, we're going to use what's called the student's tDistribution, where I mentioned this elsewhere, but I think the story behind this is a little bit interesting. It's a little bit illuminating, in particular for how notation comes to be. It involves a bit of alcohol as well.
Brilliant! Brilliant!
And anyone who wants to earn 1 point of extra credit towards their second exam can email me with a bit of background on where the distribution comes from. But even though I'm not going to talk about where it comes from here, what we really need to understand is that the t-distribution is intended for situations where we don't know a lot about the population, but still want to make some determinations about sample means. We still want to talk in terms of things like the central limit theorem. In particular, we use it for cases where we don't know sigma, but generally it's meant for cases where we have very few elements in our sample size. But in this case, we can talk about something like a z-score in the context of the central limit theorem, but we instead here call a t-score, where our t-score has the value x bar minus mu, but now divided by s over root n. So something very much like a standard error, but instead in terms of s, where in general there are a few important properties to know about the t-distribution, where we have that when sigma is unknown, the sample size is less than 30, and the random variable x is approximately normal, it follows a t-distribution. Or it's important that I say a there because because we don't really have a v for the t-distribution. I'm being clumsy with my articles, but t-distributions are not unique things. They are families of curves based around things called degrees of freedom, which I'll talk about in a second. But the measures of central tendency for t-distributions are equal to 0. The t-distribution is symmetric around the mean and has a bell shape. The total area under the t-curve is 1. And as we can see from there, we may think that this is very similar to the standard normal distribution, and it is. It has a lot of commonalities. But there are also some very important differences where, for one, the standard deviation and variance of the t-distribution are not consistent values. They vary based on sample size and are greater than 1, which is to say that we don't always have a consistent number, but it's always more variable than what we get with the standard normal distribution, which makes sense because we're talking about it in a context where we have a representation that is inherently more variable. Then from there we have that the t-distribution has thicker tails, as it were, than the standard normal, which sounds a bit inappropriate as I'm saying it now, but that's okay. Essentially what that means is it's lifted a little bit off of the axis, a little bit higher than the standard normal is. And the larger the sample size gets, that is, the more elements we have in our sample, the closer the t-distribution gets to being standard normal. And what we have here, our distribution, our t-distribution, is dependent on, as I said, the degrees of freedom, where, just so we're clear, our degrees of freedom are the number of values in our sample that are free to vary when we have a determined value we're trying to map them to. So, for example, if I know the mean of a data set that I want to work with, and I have 5 values, the first 4 of them can be whatever I want. I have freedom to make them any number that I need. I can set them to anything possible. But once I have those 4 and the mean I want to hit, The fifth is stuck at whatever value I need to put in there to make sure that I match what I'm aiming to. So the degrees of freedom in this context, we're talking about these things, is n minus 1. We'll see later in the semester there's an adjustment we can make where the degrees of freedom change a little bit, but for now, that's the sort of thing that we are looking at with our degrees of freedom and our t-distributions. So, as we're working here, let's just get a quick example looking at how this stuff works in terms of critical values. So for this first example, we want to find the critical values for a 95% confidence interval and a sample size n equals 15. So the first thing we should understand is anytime we're dealing with the t-distribution, we've got to figure out what the degrees of freedom are. Where, since we have n equals 15, that means our degrees of freedom, which we generally denote d dot f, will be 15 n minus 1, or if you prefer, and most do, 14. And from here, we need to understand that what we're getting from our tails, thinking in terms of a distribution, is that each tail will have 2.5% of data. That is, the window in the middle of 95 leaves 2.5 on each end. So if we want to get that, we can use a function that might be in our calculator, it might not be. We'll talk about that in a second. But if we have it, we can use what's called the inverse t function in the calculator, where we're going to put in 0.975 to reflect the fact that we have 95 in the middle and 2.5 on the left, along with 14 degrees of freedom to get a value of approximately 2.145 for our t-score, for our t critical value. Where it's important to know here that when it comes to these critical values, when it comes to this inverse t function, some calculators actually don't have that built in by default, especially the older ones. So you may have to put that in by hand, and I've put a video on the Canvas page for how you can do that. But just understand that that might be an issue. You may want to work with the table as well for getting that set up. I will say that it's going to come up occasionally on the homework that you'll need to find critical values for t-scores. I'm probably not going to ask it on the exam just because it's unfair with how I assume you're going to work, and this is one of the biggest issues with the TI-83 in particular. But anyway, the critical values, regardless, are really a means to an end. They're just something we use to be able to discuss what goes on with confidence intervals, and that's what we're going to see how to work with next.